Thank you very much, Marcos Penedo, for joining us today. We've been very excited to hear about a very different kind of microscopy than our other microscopes so far that we've been talking about, or bioimaging methods or open source methods in general that we feature in our LIBREhub seminar series. So today we have Marcos joining from the École Polytechnique Fédérale de Lausanne in Switzerland, telling us about a very interesting project of a scanning probe microscope that's open source. Thank you very much for joining us today.
Thanks, Tobias, for the kind invitation and introduction. So, as you said, I'm based in Lausanne at the PFL here at the university, and our group mostly work on developing new instruments that normally you cannot find on the market, so you cannot buy them, or just combine different instruments mostly with scanning probe microscopes. Here today, I'm going to try to introduce what we are doing in terms of scanning probe microscopy in open source. In fact, mostly we build our own AFMs from controller, high voltage amplifier bases, heads, and also the software, and all these different components are fully open source. I want just to start the talk with a little concept. So, well, I mean, mostly everybody knows about or have an idea of what is OpenScience. Mostly just you could think about just data or lab notes or papers or images or data methods in general that are fully available. So you have repositories, or you have freely access to publications, or you just give open source data databases. But what happens if the data is an instrument? In this case, it's a bit different. I mean, there are different approaches you can do. For example, if you're lucky and develop a new instrument that is not on the market, you can just patent it, and then you can, for example, you can register or just sell it the patent to a company, or develop it in parallel with a company, and that arrives at the end to the community, mostly the scientific community or industrial community. But there's another way. I mean, that's the way I guess most of the people who are here now is, why not just go directly to the community? So you just develop the instrument, and then you create your own community, or just look for collaborators, and you develop and share all the data related to that. So that is our approach, and the benefits, of course, are clear. First, you have a broader use. I mean, you have people, mostly collaborators, that can help you to develop further to the instrument. Of course, you get citations and publications, because it's the way science works, or the way they can measure our quality of the science. But it's also benefit to the community. Of course, you give full access to the instrument from scratch. You can just share the schematics. You can share the software. That will increase the speed of the innovation, because it's not only you, there's several people working in parallel. So you maybe are good on developing scanners, or you're good on developing a specific area of the software, but maybe another group has more expertise in developing the probes or combination with other instruments. If you fully share all the information, you fully share all the instruments, that open the window to increase the speed of developing the technique or the instrument. So in our case, and I'm gonna mostly focus on AFM, because it's the core of our project. Here in the lab, we develop fully the whole atomic force microscope. I'm gonna give a short introduction later for the people that are not familiar with that. But mostly here we have the controller, which is the one that is in charge of moving the scanner, do the feedback to generate topographic images in general. We have the high voltage amplifier, that is the one actually give the power to the scanner to do the movement X, Y, Z. We have the base here, which consists in a scanner here to, of course, move the sample, all the information about how to align the lasers, and then the head, that is where you place a little cantilever. That is the probe you use on the atomic force microscope to image. And here you have a picture of how it's inside with different lasers, different paths, and of course the scanner that in our case we developed in a way that is compatible with a high-speed AFM. So what is the AFM? So mostly is like it's coming, or it's like the origin is the scanning for microscopy, that mostly you have a probe, can be big, can be smaller, that fills the force surfaces, and these forces could be from van der Waals, could be electric, could be magnetic, capillary, chemical. They're like huge magnetic, huge range of forces you can feel. Sometimes, depending of the forces and the technique you use, you can you can address these forces, or you can transform these forces into topography of the image. For that, what do you need? I introduced it before, but mostly you have like here, like the scanner, that is the one that moves the sample in X, Y, Z. You have a cantilever, that is a lever that has at the end a really sharp tip with around 2 to 10 nanometers tip radius. The thinner, the more resolution you get, and that's the one that fills the surface. And to detect the oscillation or deflection of the cantilever, what you have is a laser that goes to, or is focused at the very end of the cantilever, and then you use a photodetector to see the deflection of the cantilever. That is the translation of the corrugation of the surface. And after that, of course, you need a controller to synchronize all these different elements, to get the data, to control the scanner, to scan the surface, to just do a feedback to generate the topography, and that is all generated on the controller. So I like to show this video because give you more insight of at the end what is that. In this case was an AFM inside an SEM, and you can see how small is the tip at the very end of this cantilever, and what you do is you approach the surface and you start to probe the surface. In this case, the technique was the first developed for the AFM, that is contact mode. You just go to the surface. You just can either read the deflection of the cantilever when it finds something. If you have, for example, a feature of the surface, it's going to bend the cantilever, and then you can generate a topographical image, or you can just keep constant that deflection moving up and down the sample. That also will be a mirror of the topographical surface. I don't have too much time to go into the different modes you have here, but this is the contact mode, is the first one and the most simple one. But you have another modes that are contact, non-contact, or you can find different names like tapping or intermittent contact, that is used where you just oscillate the cantilever, and in principle is more gentle to image, for example, biosamples, where you need to be really careful of not apply too much forces and destroy the biosample. You can use also what is called off resonance tapping. Either you can move the scanner up and down, or the cantilever, just until it deflects or reach a maximum force at the surface. And with that maximum force at the surface, at every tap, you can reconstruct the surface. But in general, you can think the AFM as a sharp rope that fills the surface or feels forces there, and from that, most of the cases you can reconstruct a kind of topography. Okay, and the versatility of this tool is because you can use it on vacuum, as I said, as I showed in the previous video, inside an SEM, in air, and also in liquids. It's independent of the medium. It's kind of huge range. I mean, if you don't use a medium that can corrode any of the elements on the microscope, the AFM will work there. So that is great for biology. I mean, you can see here example of different molecules from DNA to viruses or cells, bacteria you can image with the AFM. But another thing is You can design special scanners that can move super fast, and you can do high-speed AFM. So you can generate up to 20 or 50 frames per second. And here is a good example on this video here on the bottom, where you can see the myosin working on the actin fibers, typical thing you see on the books. But here, in fact, you can see how it's really moving through the fibers. Just coming back to our platform, we have different pieces in our platform, and one of the advantages is that they're quite modular. Even some of them, for example, the controller or the high voltage amplifier, can be used in another system. You don't need to use our AFM head or our AFM base. Those controllers can be used with commercial systems, and that gives you the potentiality of course, if you have an AFM that has a specific modes or a specific ways of work or techniques, you're not constrained to what the provider gives you on the software. So you can develop your own modes. You can just develop fancy experiments because you have full power as you have the controllers yourself. Okay, in our case, we have the AFM head that is prepared for high speed, and for high speed, you need to have small cantilevers that has high resonances. That is important to be able to move fast. And for that, we need to have a small spot size. And with our head, in fact, we can get a spot size of elliptically 4 micrometers long and 0.7 micrometers wide, which is enough for the smallest cantilevers you can either fabricate or use. Then you have a high-speed scanner that has a special configuration that can reach higher frequencies, have resonance frequencies and XY higher than a few kilohertz, and instead higher than 50 or 100 kilohertz. With that, of course, you can do high feedbacks and you can just image fast. Then you have a base unit, and the base unit is mostly consistent in a scanner and also a motor approach. So you have to have the cantilever and the sample, and you have to do a safe approach until to reach the surface. That is an important part of the measurement. You have to be careful and have a stable motor that doesn't crash the cantilever into the surface. And then we have our low voltage controller. It is based in National Instrument FPGA that we program ourselves, and we created our software, and can go up to 40 mega samples per second. That is important for high-speed AFM because you use high frequencies, and can generate up to 8 million pixels per second. That gives you the ability of have different channels of information, not only topography, but you can have electrical, magnetic, mechanical properties channels that are important sometimes because you want to correlate topography with something else. And finally, we have the high voltage amplifier that has to be the bandwidth high enough to just be able to move in XY quickly. So the bandwidth here is 7 kilohertz in XY. So it means you can do up to 2000, 3000 lines per second, and 500 kilohertz on set give you the ability to really go fast on the topography feedback. Then within our controller, you can see on the left, this is the FPGA. The FPGA will be here, and then you have a laptop board that translates the voltages on that FPGA from National Instrument to the voltage you need to, or you use on your microscope. And then we created, we plug a motherboard with little daughter boards. The idea of this is in these little daughter boards, you can do some conditioning of the filter of the signal. You can do some filtering of the signal, and that sometimes is important because not everybody has the same requirements. For my case, it could be like a need to have a high pass filter of 10 kilohertz, but someone else maybe has a requirement of having the other way around, low pass filter of 10 kilohertz. And for that, it's nice to have, okay, I have this channel, and then I can plug a daughter board that I design myself with this requirement. I don't need to change anything else. That's the beauty of this. So we have modular for different parts. We can plug on the different channels. So this FPGA has up to 8 analog inputs and 8 analog outputs. So that gives you the possibility to have 8 different channels. And with that architecture, you can change or you can adapt the requirements of each channel for your experiments without any need to change anything else on the whole controller. Then the software, as it is national instrument, we fully program it in LabVIEW. It's true that now we have not only LabVIEW, we have different parts written in Python and also in C, depending on the requirements, but the whole core is mostly written in LabVIEW. So of course, if you need to do any changes in the code, you will need to have LabVIEW licenses. But if you are just only a user, we also provide a compiled version that doesn't need to have any licensing with LabVIEW. You only need to have LabVIEW runtime environment that is for free, in fact. So we have kind of 2 codes. One is mostly for developers. In that case, you need to have LabVIEW, and the other one is mostly for the people that are mostly users or images that they don't do any developing. And for that, we can give already the pre-compiled version, the executable, that doesn't require any licenses in lab. So the idea of our software is a bit like the hardware. We like to have different modules. So the reason for that is like this: if you need to add something else or if you need to modify something for your specific requirements, you don't need to change the whole code. For example, here on the FPA part, we have different modules that take care of analog inputs, analog output, the scan engine that is the one that is in charge of the XY generation, PI controllers. We have also filters, but all of them, they're in different loops in different parts of the code, and then can be modifying themselves without the need of modify the rest. Even if you want to add a new technique or a new mode on the SPM, you don't need to rewrite everything. We already provide a way to just adapt or just embed your requirements in one specific part of the code, and that will make everything working. And on the front panel, means on the computer side, is the same. We have different kind of windows of the eyes for different things. So for the scan generation, for the scan control, like start the scan up, down, stop, pause. This is speed, this is point. So everything is in different compartments. We have different compartments for littlescopes to check signals, for the monitors to check images. An example of the code, and already you can see the different windows that relate to different aspects of the software. So here on the right, you have the monitors that, for example, in this case was simple grid. So it shows the topography here, and you can, of course, change the colors, do some processing. Of course, the data saved is going to be always raw. Here you have the scan parameter like pixels, angles, width, speed, or the file you save it. Here you have, in case you want to do another kind of modes different to contact. So the signal generation. Here the set control for the PID control to generate the topography, and so on. Here are the little scopes. The idea of all of this is, again, if you need to add another, for example, another module for your specific requirements or experiments, then you don't need to redo anything. You just create your own window that has access to all the signals on the controller, and you can create your own mode. An example of this is, in our case, we have an AFM inside of SEM. And for that, we wanted to control not only the AFM, but also the SEM with our controller, and was literally kind of copy-pasting the scan engine, the one in charge of moving X and Y, on another one of the outputs of the controller. And then already we have here, you see here a second control for the SEM, and here you have an example of an image with the SEM. At the same time, we're doing here the AFM. We didn't do any change, just kind of copy paste on the FPGA the scan engine, the one that generates XY pattern, and we create a special monitor to read for another input, and then that's it. So that's the beauty of this, that you can just adapt this controller for different instruments. In this case, for an SCM that had an AFM inside. But not only that, we also create using an optic device, a nano manipulator, so we can use the cantilever as a nano manipulator. And for that, again, we didn't need to do any change on the code, but just add another VI, another module that controls this and talks to the FPGA. About the file formats, we have two file formats to save. Following our open source philosophy, we use Gwyddion. Gwyddion, well, if you work in the SPM community, it's a well-known software that is open source and they share everything. So by default, we save the images in Gwyddion, but also we save the images in HDF5 format as well. That is an open source format file. Mostly we created or we add this format because for large files, Gwyddion is not able to handle files larger than 1 GB. And for example, this is an AFM image that has 20,000 by 20,000 pixels, so 400 megapixels, and with Gwyddion we're not able to handle it, but HDFI is able to save that image and then to just recover the data. But again, you can choose within these two file formats, but even if you want to add something else, it's just quite easy to add another file format on the software. And of course, as I said at the beginning, it's really important to have a good documentation, something we are working on. Our idea, we already have kind of a manual, but is to have also more diagrams, have also create videos to explain how to use the software. And we what we started also last year is just to have a GitHub account for that. Still is not open in the sense that it's not public, but if you want or you are interested on the software, you can write to me and I can just add you to the project, and you are fully it's fully available for everybody that wants to check and take a look of the software. But our idea is with GitHub, we have different collaborators around the world, and we can just work in parallel to develop the software. But it's also easier to install in other computers. The software just kind of pulling the software from the GitHub, and also for that date makes everything more easy. But as you see here, is what I said at the beginning. We have kind of two GitHub repositories, one for the source, it means for the developers, and the second one is just the executable. It's just for people that wants to use it only for imaging. And well, here's kind of summary or a brief of the different modes we have already installed. This is done with contact mode. Here you can see like this structure or this pattern. You can see the resolution here. I mean, there's a periodicity of 17.7 nanometers. We can do also tapping mode, where you can use the phase to get viscoelastic information of the samples. We use a mode we develop here for the thermal of resonance tapping mode. Here's an example of DNA on the surface and mica. And also we can get not only information about the topography, the height, but we can get mechanical information. Could be addition, could be jump modulus, could be dissipation. So that are kind of the different modes we have implemented that can be used for different things on the AFM. Apart from that, here we already install, or not install, but we already have some modules for doing to do KPFM and to do MFM. KPFM is for electric measurements. MFM is for magnetic measurements. You can get at the same time you get topography of the surface. You can get also magnetic and electric information of the samples. And as I said, our controller is not restricted only to our FM. We can use it, or it's adapted to any simple to other commercial systems. Here are different examples of the commercial systems we already use, or they are adapted to our controller. from Bruker. We use it already with a multimode, with a dimension 3100, the bioscope. We use it also with Nanosurf instruments, DriveAFM and FlexAFM, QT microscopes that are the AFM inside the CM also. In this case, in fact, is a collaborate. They're collaborating with us. They are selling in their products our controller right away. So that's an example of, okay, this open source is not only restricted to let's say community that shares at the university or other places the ideas. We can also collaborate with the industry. They licensed our controller and they sell it with their products, which also broadens the usage and scope of the controller. We also use our controller with another AFM that is used inside the CMs, that is the Litescope for Nenovision. We also control Omicron STMs, and well, this is a Zurich instrument locking amplifier that is controlled also with our software, and the Witec Alpha SNOM, that is another kind of SPM technique, and of course the SCM I showed you at the beginning. And what we're doing now is try to adapt our system to PARC and to GPK, that are also important brands and SPM. Okay, just to show you a few samples of what we do here in the lab. These are kind of images of the SAS6 assembly. The SAS6 is the different rings that are on the centrioles, and here an example of the assembly taking with our controller. And here you can see we can reach up to 10 frames per second when we do 50 by 50 pixels, but you are able to see how is the assembly of this ring structures in time. So the resolutions around 10 frames per second is, you can take a frame every 100 milliseconds, but we are able now to go down to 50 to 20 milliseconds per frame. But it's not only restricted, or we don't do only AFM here. We do other techniques. Here I'm showing you a scanning ion conductive microscopy, SICM. In this case, instead of imaging forces here with a tip, what you have is just a pipette with an electrode inside. I'm just putting a potential over there, where you measure a current. So you have a flow of currents or ions through the pipette, but imagine you get close to the surface at some point. You constrain the space where the ions can flow through the pipette because they're closing, and the last hole of the pipette is close to the surface. So the current starts to decrease, and that is the signal you use for the feedback. The advantage of this technique compared to the AFM is that it's a pure not contact, because you always stop before touching the cell. So what you do is you feel kind of a few nanometers away the cell, and then it's totally ubiquitous for the cell, and you can do kind of these measurements over time. You can see on the right an example of these nice images renderings of how the cells are moving or develop over time. But we don't use these pipettes only to do imaging. We do also spectroscopy. You can think, if you put DNA at the surface, attached to the surface, then you can use this pipette to probe it. And as I said, what you measure is the currents over the pipette. If you have proteins attached to the DNA, when they are really on the hole or on the aperture, they're gonna decrease the ability of the ions going through the pipette, and you're gonna see these dips on the signal. So with this, you can do some kind of spectroscopy on this DNA using these pipettes. And for that, we can we use also our controller. We have different modules for that. So I keep saying the modularity of our design lets us to add different modules without needing to redo for every single technique the whole software. And another example is what I introduced before, a little bit. So we have this AFM inside the SCM. Mostly you can think this system as you use the SCM as your eyes when you need to do an AFM measurement with the tip in a specific place that is different to find because it's like a really rough sample, or has like a little, or the region of interest is a little area where you need to have a nanometer eyes to see where to image. Then it's a good idea to use the SCM. And in fact, this AFM now is a product from Quantum Design, and we develop both the the hardware, so the AFM itself, and also they sell it with our controller. Here you have a zoom in of the. Here you can see the cantilever, and this is the sample holder. And here in this needle you see is if you want to, for example, inject some gas to grow structures, is also compatible with that. Here's an example of what I was saying. We were able to image with the cantilever the eye of an insect. If you place this insect, for example, in a normal AFM, it's difficult to just go with the tip to the specific place and measure, because you have a big insect and it's really easy to break this tiny cantilever just looking for the right place. With SCM, it's quite easy. So you have a safe distance with SCM. You see when you're on the right spot, and then you go down, and then you can start to do the AFM image, and also give you more scales. One of the drawbacks of the AFM is that it's difficult to get images larger than 100 micrometers by 100 micrometers, but the SCM has a large XY field. So in fact, you can use, this is the SCM image, you have an image of the area, then you can even zoom further with SCM, but at some point you cannot get good images and you need more resolution, and for that you can go with AFM. That is here. Here you have the different cells on the hexagonal lattice on the eyes of this insect, and then here you have an image of the cones that are the photoreceptors on this side. So the idea is you have the AFM as a final image tool, but you use the SCM as UI to go through or to navigate through the sample. But again, one of the advantages is we can do really real adaptation of our requirements with our controller. The technique I showed you before, the SICM, has the drawback of super slow, but as we have the power to modify everything we need here, what we did is, okay, why don't we just skip some lines of the image and then try to reconstruct it doing some machine using some machine learning models. So this is the top one, in fact image we took. So you see these black lines are the skip ones, and then we use this method for this machine learning algorithm, and you see the reconstructed ones, and they were fixed cells. So we wanted to compare how it is in fact the real one, and we take the image after, and you can see by eye there's not any difference, and well, of course we use different statistics to see, and it quite works well. So in this case, it reduces images. Normally it was around 20 minutes every image in this technique. For these large areas, you have to go slower. It was reducing to 13 minutes. Again, I showing this just to say, for that we didn't need to do a huge change of the software. In fact, was a few lines on how is the data treated, or the stream data coming from the controller. Just with these few changes, we can just reduce almost 30-40% the time required for the image. But now, of course, there's a huge boom in all this machine learning or artificial intelligence. And in a conference, I met this person. This is a postdoc is in the States, is Liu, and he was showing that he was controlling a commercial AFM with Python. So was kind of doing some automation or automatic control of the system. So instead of you sitting there controlling the PI parameters of the feedback and the set point. He just created an algorithm that optimize all the parameters and do the measurements for you. Even looks for the areas of interest. And was mostly at the same time I had similar ideas. My idea was, okay, why not have an APA written in Python? So for all these people working in machine learning or artificial intelligence, if you do a script around controlling an AFM, you don't need to change that script for every different brand. You don't need to rewrite the script to adapt to the different APIs you have for the different microscopes. So you sit there and you can have the Python code and you run it there because you use or you have a kind of same APA. So talking to him, we decide, okay, let's try to do it first in your controller. I had to do some adaptations you see here because mostly I have to do a call from Python and then translate that call to something that the controller understand. But it's mostly like kind of I send text messages for the different commands and then I do an action on the library software. And with this Python APA I created, the idea is, okay, it's of course super useful for creating Python scripts to have controls, but the idea is also to create your own GUI. So at least from our experience here, I mean, some people, they don't need not even 50% of the code we need or the GUI we have created. And like this, they can create your own GUI. I mean, if you need only literally a literal scanner plus a few modules, you can create in Python your own GUI. You don't need even to create anything in LabVIEW because you have already this running on the background. You can communicate with that, and then you can create your own needs in Python. That is a language that is more common in the scientific community. And of course, for that, we created another project in GitHub. This is fully open. If you are interested, you can contact me. But we already contacted some companies, SPM companies, AFM, Nanosurf, Asylum, Quantum Design, and Nenovision, and they're really interested in that idea on just having kind of the same API to control with Python their instruments. And well, now we're working on that. At least this is an example now in our controller is already working, it's totally defined, and the idea is to translate that to the other controllers for the other AFM systems or distributors. And you can see that we created in a way super simple. You just create, let's say, the experiment with this object, and then you can set width, offset, scan speed, the mode, or change the set point and scan down, wait until the scan is done, and then you just get the image and you plot it or you print it. It's quite easy. I mean, all of this is exactly the same that going with the mouse and click on the different buttons and do the experiment. So it's kind of can make everything more automatic. And also, if you want to use this kind of machine learning methods or artificial intelligence scripts, you can already right away use it in our controller. The idea is to use it in the others. And this is exactly the same video we saw at the beginning, but this is running in our controller. So at least we have already Asylum and our controller with QD as well that runs with the same API. But the idea is just to grow this, to just bring other companies here and try to have the same kind of API for all the systems. And but we don't want only that. So now we thought, okay, it's nice to have these scripts. So you can create your own script for automation of the different tasks. If you want to do spectroscopy, you don't need to click 100 times to do 100 times a curve. You can write a script that goes here, and there, does the spectroscopy curve, and then continues doing imaging. Or if you want to do different images in different areas, you can just run the script to do that. But it would be nice if instead of you need to write the script, you can write in a natural human language. Please, today I want to do this, this, and that. Please generate the code and run it. So that's the idea we're trying to, or we are working on. That now is just instead of even need to write the code in Python, just be able to do all the tasks, writing this in human language. And even the next step will be like, instead of even writing, just tell it, just please, today I need to do this, 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 and that experiment. I need to do a sweep in areas from 100 nanometers to 2 micrometers, moving the offset 100 nanometers. So just do everything more, easier for the user to use the instrument. We already have kind of a proof of concept where we developed a language interaction using ChatGPT 4.5. You have a custom training API, and that then is generating or the code to communicate with the LVNI controller. So we already have a kind of, right now it's a bit simple, but a way you can write, please do the 200 by 56 pixels by 256 pixels of an area of 2 micrometers at that speed with this set point. So, but the idea is be able to train further this and be able to do more specific tasks or more complicated tasks. And just for finalizing the talk, I want to talk a bit of the different collaborators or systems we have around the world. We have up to 10 setups in our laboratory, but we already have collaborators or setups in other countries, in Switzerland, USA, China, Austria, India, and so on, that are either using our systems or contributing to develop further the software. We also, as I said, we have a part in a commercial microscope, the quantum design, the AFM, the AFM inside the SPM. They sell our controller with the products. And and what we do also is, okay, not everybody knows how to build from the schematics. We provide workshops in a yearly basis, so we can we just host groups of 2 to 4 people where they come here and they build the AFM, or they build the controller, or high voltage amplifier all at the same time. So they come here for a week and we just buy in advance all the different components, and we just help them to build the different parts. So the idea of this is, of course, some people are scared of building, but it's at the end it's not so difficult if you have, we have the manuals, but if you have the help here. And the advantage is once you build it, then you understand mostly how it works, and then you can keep it. Because the problem, we could build the systems, but then if you have a problem and you don't have a knowledge, or you didn't know how to fix it, then in our experience, people stop to use it in a while. And also last year we have a conference trying to bring the most important SPM builders around the world. So to try to push them to embrace a bit the open source philosophy, trying to share more the builds or the setups that they have in the systems, try to even create the standards. Sometimes it's difficult to compare different systems, the specs, because of course you try to put the specs in the way they look prettier on the papers, but at the end is difficult to compare the different systems. And also we try to have some kind of standards, mostly in connectors and in cabling, because like this, if I develop, for example, a locking amplifier, then it's easy to connect to another system from another group, because we share the same standards. The voltages, the level voltages are the same, the connectors are the same, and so on. And again, as we see, this project is, we create a playground SPM for development. So we have like kind of a modular framework where you can add new imaging mode, film mechanism, scaling trajectories, or automation of operation, and so on. You can combine this system, not even the whole thing, but different parts, like only the head, only the controller, only the high voltage amplifier, or only the software with different parts. And here it is like, of course, it's a project with many people involved. Here are like the students, postdocs, scientists involved in our lab for the last 4 to 6 years. That is when we started with that. And yeah, thanks a lot for listening to me. I hope it was not so long. And of course, if you have any question, I'm happy to answer them.
Thank you very much, Marcus. That was very fascinating. It's incredibly powerful, the platform that you built. I'm really amazed by the quality and how you managed to put it into an SEM. That's very impressive, I think.